Okay, hello everyone, and welcome to today's lecture. So, we will pick from the same point where we left last time, like on last Thursday. We were basically discussing about the memory, the characteristics of memory. Uh, so, before I start today's lecture slides, are there any questions regarding previous lectures? And it looks like number of participants today is relatively low, only 30, while 45 students are registered. I hope there is no issue in accessing the Zoom link. It should not be because last time most of the students, like 45, 44 students were present in the online meeting. So, uh, was it because you had a quiz? That's why. Uh, okay, let me quickly check if I have received any email regarding difficulty in accessing the Zoom. No, no. Okay. So, mm, okay. So, can you please confirm if you can see my slides? It should be displaying memory component or characteristics of memory. Yeah. Okay. Thank you. Thank you. So, okay. So last time we were talking about components of microcontroller. Actually, the microcontroller which we are going to study. And the one component that we was studying was the memory and how we can characterize it. So the first parameter, or the first characteristic is capacity. So which is always given in number of bits. Remember, not in number of bytes, right? So when we say 128 kilobits, so it means there are actually 128 times 1024 bits available. Second thing is organization, which basically tells you that how memory locations are organized, just like shown in this figure here. Uh, that if you have a memory which is 128 cross 4 memory, then it's mean there are in total 128 locations starting from 0, and then each location can store each location can store 4 bits. Okay, not 4 bytes. Each location can store 4 bits. Okay, and access time is the time that is needed to read the data from memory. Remember, last time I explained that access time is measured as a latency of the read operation, not as a latency of write operation. Why? Because from the processor perspective, read is more critical than write, because if a processor says that, okay, I need to read the data into a register and then it needs to use that register, it cannot simply put the read request and then continue, because then it has to use that data. So it cannot go to the next instruction until the data becomes available. However, in case of a write, a processor can say, okay, I just want to write this data in the memory, and if processor is writing the data, it's mean the data is already available in the register. So even if it needs to use the same data in the following instruction, the data is already available in the register, so it can use it. So it doesn't need to wait for the write operation to actually put the data in the memory. So it is not critical from the perspective of the processor. That's why we measure the access time of a memory in terms of the read operation, not write operation. And it is normally given in nanosecond scale. And one nanosecond is equal to 10 raised power minus 9 seconds. Okay. Uh, then we talked about the pinout, a typical pinout of a memory chip. So we said that any memory, it will have definitely the data bus. Now the width of the data bus, which basically tells that how many data pins are there, it depends upon how many bits can be stored in a single location of the memory. So for example, in previous figure here, we said that in this example, we said only 4 bits can be stored in a single location, which means that the width of the database bus for this memory will be 4, right? But in this example here, we have data bus with a width of 8. So which basically means that each location inside the memory, it can store 8 bits here. 8 bits, okay? The second bus which every memory will have is the address bus. And again, the width of the address bus, it depends upon the number of locations available in the memory. So for example, in the previous example, we had 128 locations, right? So it's mean we need enough number of address lines to locate 128 locations. And how we can find that? By finding the log of 127 to the base 2. An easier way to say is like this. Remember in previous lecture, we talked about weights of the binary, right? So we talked about the weight of the first digit in a binary number. Our first bit in a binary number is 1, then 2, 4, 8, 16, 32, 64. You can continue like this. 64, and then you have 128, right? So you can count actually. So let me count 1, 2, 4, 8, 16, 32, 64, 128. So you will actually need 7 bits. 7 bit to access 128 locations. Because if you have 7 bits, then you can in total have 128 different combinations of zeros and 1, right? So it will be 2 raised to power 2 raised to power 7. So if you find 2 raised to power 7, 1, 2, 4, 8, 16, 32, 64, 128. Yeah. Yeah. 1, 2, 4, 8. 1, 2, 4, 8, 16, 32, 64, 128. Sorry, I think it will be, you need to do the math. Yeah, let me do it here. So if you have, or maybe I can go to Notepad. Discard. Again, please send me a text to confirm that you can see the Notepad. Not OneNote. Okay. Okay. So let's say if I have 7 bits, I have, let's say, bit 0 to bit 7. So in total 8 bits. So what I can have 1, 1, 1, 1, and then 1, 1, 1, 1. Now I'm not writing all the weights. I will write only most significant bit. Most significant weight 1, 2, 4, 8, 16, 32, 64. Now here I have 64, right? And then I'm going toward the right. So next weight on the right side is 32 plus 16 plus 8 plus 4 plus 2 plus 1. Can anyone do math for me and sum all these numbers? If you are done quicker than me, then let me know. 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is, yeah, 127. Yeah, so it is 127. And since we also have a bit combination where all the bits are zeros, so we need only, yeah, thank you. So we need only this number of bits. Let me draw here. We only need this number of bits, which is actually 7 bits. So we need 7 bits to address 128 different locations, because you have also combination of bits where all values are zeros. So all zeros to all ones. So you will be able to address the 128 locations. Okay. Now, okay. So we were talking about the number, how many address bits are needed. So number of address bits you need on a memory, actually it depends how many locations you have within the memory chip. So in the previous example, if you have 128 locations, so it means you need 7 different pins in the address bus, or the width of the address bus is 7, right? So if you like, let's say you increase the number of locations, so from 128 to 256, then you will need eight pins in the memory bus, sorry, in the address bus, or the width of the address bus will be 8. Okay. The other, so these are known as like data bus and address bus, and beside that you also have a control bus. So control bus is consisted of three different signals, these ones. And last time I explained their functionality, but let me do it again quickly. So write enable, so all of these are low active. Low active mean that uh, they they work, or they achieve their function specified functionality when the input value is 0. Okay, so when you put 0 here, so maybe I can start with chip select. So when you put 0 here, it's mean you are saying enable this whole memory chip, right? If otherwise, if it is 1, it means that this memory chip will not be able to perform a read or write operation. Now, first thing you need to do is you need to enable the chip or select the chip. That's why it is named as chip select, by sending 0. And then once the chip is selected, then now you can do two different operations, right? You can do either a write, or you can perform the read. So if you want to do the write, then you will put 1 on this output enable signal. Output enable signal mean that enable the data to become available on the output, which is data bus, right? But we are doing the write operation. So we will make this signal 1, and we will put 0 on write and write enable, because we want to put the data from the bus coming from the CPU to the memory. So then whatever data you are placing on the data bus will be written on the given location, which is specified by the address bus. On the other hand, if you want to do the read operation, so still you will have 0 on the chip select, but you will put 0 on the output enable, which basically you are saying that make the data bus enable, so that it can carry the data, which will be uh, outputted by the memory chip. And here you will put 1, which basically means that I am not going to write the data in the memory chip. I want to read the data from the memory chip. Okay. So by the way, you can stop me anytime when you have a question. Okay. Now, how we connect memory and CPU? Actually, it is explained already in the previous slide, but let me go little bit more, explain a little bit more on this slide. So VCC, it is always connected with the power supply, uh, ground with the ground negative power supply pin, which is normally connected with 0, on negative power supply. These D0 to D7, these are data bits or data bus from bit 0 to 7. So in this particular example, it is 0 to 7, but I mean, depending upon the chip, it can be larger than 0 to 7, like maybe 0 to 15 or 0 to 3. Depends how many bits are stored in a single location of a memory. Then these A0 to AN-1 are address bits. This is write enable, it is low effective. Output enable, it is low effective. Chip selection, a chip select, and it is also low effective. Remember that anytime if a signal has a bar on it, it's like here, right, and on the top of the write enable, you have a bar, or on top of OE, you have bars similar for CS, then it's mean that that particular signal is active low, which means that it will work when the value of that signal is 0, and it will be disabled, or it will not be activated when the value of the signal is logical value of the signal is 1. Okay. Okay, so this is actually we have seen already this figure. So now we are going to talk about how the read operation happens. When we want to perform a read operation, then how different signals their value changes over time. Okay, so in this graph on the x-axis you have time, and it is increasing on the rightward direction, and on the vertical axis you have voltage, so it increasing in the upward direction. Okay. So first, when you want to perform a write, first thing you need to do is that you need to put the address. And when I say you, it's basically means CPU. So CPU need to put the address on the address bus. So here CPU will put the address, and this is where it is happening. So here the value of the address bus is changing, which basically mean that previously it had some other value, some garbage. But then at this time point, we are the CPU puts the actual address from where actual address at where it want to perform uh, a read operation. Okay, so here you are putting the address, but then that is not enough. After putting in the address, what you need to do is that you also need to send a zero signal here on the chip select. So this is where you are reducing the value signal value to from 1 to 0. And then also, since you are going to read the data, so you also have to send one on sorry, 0 or active low on this signal, right enable. Sorry, on output enable, not right enable. So here you are setting its logic value to 0 from 1 to 0. Okay, and then uh, after that, after you have applied correct voltage levels for all the control signals and you have also placed the address, then it takes some time, after which your data will become available on the data bus here on the output, right? So you can ask question like, for example, why there is a gap between when we set the address, CPU sets the address on the address bus, and then the chip select is not immediately set to 0 at the same time point, for example, not at this point, and output enable is also not set at the same point. Because the internal logic of this memory chip, it takes some time before it can actually internally latch the address, or it can read the address. So if you, for example, set the chip select signal or output enable signal at the same time point, but the internal circuitry of the memory chip has not yet sensed the new address which you have placed, because it takes some time for it, then maybe it will give you the data on the output which corresponds to the older address, for example this address. So the address needs it takes some time for the address values or address signals to be stabilized in the internal circuitry of the memory chip. And same is the case also for from the chip select. So like immediate, you can also again ask, why can't we supply the chip select, make the chip select and output enable active low at the same time point here? Why there is a gap? Why there is this gap? Again, the same reason, that it takes for some time for the memory chip to sense the low value of the chip select. Okay. And then once you have applied all the signals, then it takes some time, and after that the data will become available on the output bus. Now, how we measure the access time of the memory chip? From the time point where you made the address available here, from this time point to the time point when valid data becomes actually available on the output or the data bus. So this is your access time. And our write enable signal, it remains 1, which means disable here, right? Okay. Now, how can we uh, okay, how the signals are different, how the signals change their values when we perform a write operation on the memory chip. So let me just simply change the color of marker. Okay. So this time we are going to perform the write operation. So again, first your CPU puts the address on the address bus for the location from where it wants at the location to which it wants to write the data. And after some time, after some gap, it selects the sets the chip select signal to 0. So this is again 0, right? And then uh, also after some time, after like setting the chip select signal, you need to make the write enable 0, so that you can tell your memory chip that we are going to write the data. And once you have applied all the correct values for the signal, then it takes some time, after which your data becomes available. So here, this is the time, data setup is the time which actually takes the time which is needed by the memory circuitry to make the data available on the output. And then the data must remain valid for this period of time so that it can be read by the CPU. Okay. So, but again, as we said, as I said, that we measure the access time uh, as latency of the read operation, not as a latency of the write operation. That's why in this figure you don't see that measurement of memory access time. Okay, so in the like previous figure, the figure which we saw in the previous week, we said that on this microcontroller you have different components. You have CPU, you have memory, you have IO peripherals, and by IO peripherals we mean different kind of external devices like mouse, keyboard, sound card, graphic card, network. Now definitely on the microcontroller you cannot directly connect. You cannot connect network. You on the chip you don't have graphic card, a network card, a sound card. But in a general purpose CPU, you have the possibility to connect these devices with your CPU. Now the question is that how we do these connections between CPU and the external devices. So if we need to connect these devices, it means that our CPU have to have a lot of pins, right? Which is a bad thing. Why it is a bad thing? Because as a rule of thumb, more pins you have on a chip, higher price it has, more expensive it becomes. That's why when designers are making chips or designing chips, they want to keep the number of pins as low as possible. Okay, so if that is the case, like uh, if the target is to keep the number of pins low, how can we achieve that while also making it possible for our devices to be connected with the CPU? Okay, so just like first thing, just like memory chip, any IO devices also need three type of connections. One, your address bus, data bus, and the control bus. Why? Because just like a memory chip, what is the purpose of an IO device? What we can do with an IO device? We can we can do a read or a write operation on an IO device, right? Depending upon the type of device or type of the device. For example, if it is a keyboard, so CPU can read data from the keyboard. But if it is a screen or a monitor, then CPU can only display the data on this particular type of device, right? And then maybe there are also some other type of devices which can perform both input and output, right? So we need one thing is that we need the data bus, irrespective of whether it is an input device or output device. We need to have the data bus either to send the data or to receive the data. Second thing, we need control bus to specify whether we want to do a write operation or a read operation on a given device. For example, if it is a keyboard, we are going to do the read. But if it is a, let's say, screen of your laptop, then we are going to do the write operation, right? The other thing is that we need address bus. Why we need address bus? Because let's say if we are in a situation where we have connected only one IO device, then it's mean that we don't need to select among multiple devices. So in that case, we don't need any address bus because it will be uh, understood that whatever data we want to read and write, it will be destined for that particular device because we have only single device on the system. But if we have more than one, then we need to select among them. And how we can select? Again, by using the address bus, right? Just like in memory, what is the job of the address bus? To select the locations, right? Like for example, remember in the previous example, we had 128 locations. So depending upon the value of the address, we will go either to location 0 or location 1 or location 2. Now you can use the same analogy to consider or replace each location with an IO device. So if let's say address is 0, go to IO device 0. If address is 1, go to IO address 1 and so forth. So on. Okay. But the thing is like we need to interface with the same CPU, not only the IO devices, but we also need to interface the memory, right? So already, for example, we need an address bus separately for the memory, a data bus for the memory, and now we also need address bus and data bus separately for IO devices. So it means that we are increasing number of pins on our chip. which is a bad thing, and we don't want to do that. Okay. So then the what we can do is that we can use actually we can share the same address bus and data bus, right? For example, you can simply treat memory also as a IO device, right? Just like here, you can put another block and name it as memory, and then the same address bus can go to the memory, same data bus can go to the memory, and also the control bus will also be same, shared, right? So this is what we are doing here. You have same address bus shared among IO devices and memory, same data bus, and also the same control bus, right? But then the question becomes that how do we manage the address conflict? Before I explain that, before I answer that question, are there any questions, comments, any confusion until this point? No? Okay. So now if we are like, we said, okay, we can share the address bus and data bus then, but the question is now how we can, how do we manage the address conflict? For example, if the value of the address placed on the address bus is 0, so what does it mean? Is does it mean that we are going to write at the location 0 of the memory chip, or we are going to read or write data from the IO device ID 0, right? How we like answer this question, how we figure out that the data that this address is like destined for which particular device, memory device or IO devices. So what we can do is like we can add another signal in the control bus and name it as IO slash memory. So remember, note that there is a bar on the memory, but there is no bar on IO, right? So, and then we can use, I will explain what is meaning of this, but let me first just highlight that how this signal is connected. So this connect signal is going to the chip select of the memory, and it is also going to, let's say we have chip select or enable input of these IO devices. So it is also going to the enable input of the IO devices and to the chip select of the memory. So now we can say that if CPU puts 0 here, which mean that it means memory will be selected because mem is here active low. So here when we select 0, so it will go to the chip select, right? And when it puts 1, then it's mean that we want to access one of these IO devices, right? Which one, which IO device? Because again, we need to answer that question, because if it is 1, then it is going to enable of all the IO devices. Now, what if we want to select a particular IO device? We will answer that question later, but for now just try to focus on the fact that we have just added one more signal in the control bus, and if its value is 0, then it's mean that we are going to select the memory, and if it is 1, it's mean one of the IO devices will be selected. Okay, but again, the thing is that uh, the addresses which are generated by the CPU, they can be in a range longer than the number of locations available in a memory chip. What does it mean? What I'm trying to say. So keep in mind that same example from our previous slide where we said that we have a memory location, or maybe we can simply follow this example. So we have memory which has only 16 different locations, right? So like from 0 to 15, right? And let's say the address range which is generated by the CPU is 0 to CPU can generate addresses in the range of, let's say 0 to let me keep it simple. Let me make it 32. How can I erase? I can't erase, I guess. Okay, so let me write again. 0 to 32, right? So in this range, we have addresses. For example, I have address uh, uh, 0. Let me go back to the notepad because it's difficult to write here. Okay. So let's say you have this memory, and this memory has only 16 locations. Let's say I'm numbering them from 0 to 15, right? Now, this memory has an address bus. So how many bits, how many signals we have uh, in the address bus? What is the width of the address bus? Can anyone, does anyone want to answer? If yes, you can just put in the chat box. What is the width of the address bus for a memory chip with 16 memory locations? If no one wants to answer, it looks like no one knows the answer. If you don't understand, then let me know. I will explain again. I will not jump to the question. I will not jump to the answer. Yeah, 4, but how we know 4? So 4, because how many locations we have in total? 16. They are numbered from 0 to 15, but there are in total 16 different locations, right? Now, 2 raised to power 4 is 16, right? That's why we are saying 4, right? But how can I go from 16? So here I'm saying, okay, from 2 raised to power 4 is 16. But question is how I can go from 16 to 4. So for that, you can simply do, if you want, log of 16 to the base 2. So you will, when you do it, you will get the value of 4. But with the practice, you will, yeah, with the practice, you will find that actually 2 raised to power 4 is 16. That's why we need 4 bits or 4 address lines to address 16 different locations, right? Okay, so the width of the address bus is 4, which means that the range of the addresses which this memory can take care of are from 0 to 1, 1, 1, 1. So in hexa, it is 0x0 if I write in 8-bit binary, and 0x0f, right? Now let's say that my processor generates the addresses in a range from 0x00 to 0xff, right? And example of only 2 addresses in this range are, let's say, if I write in binary, or let's say if I write in first in hex, it will be 0x0c, and another address in this range will be 0xf0, right? Now this address will be, it actually belongs to this memory chip because it has 16 location, right? And this is 12 if you convert it into decimal, right? But this one is greater than 15, right? So I don't want to convert into decimal, but it is greater than 15 because it is more than 0x0f, right? It is more than the upper limit, right? So now let me go back to the slides. So now when I send an address on this, bus, how this memory chip will know whether this address, the address value is meant for this particular memory chip or not. Now it should work like this, like if the address is in the range of the range of the memory chip, like from 0x00 to 0x0f, then this chip should be selected. But if it is not, then this memory chip should not be selected, right? Is everyone with me until this point? If you have like any confusion or you think like I am talking something rubbish, please let me know. Okay. So I just want you to appreciate this fact that we need a mechanism such that it makes this memory chip to be selected if the address placed by the CPU is in the range of this memory chip, like in our example from 00 to 0F in hex. But if the address is out of range for this memory chip, which means if it is greater than 0x0F, then this memory chip should not be selected. It should never receive a 0 here, right? So in other words, we want to develop a logic circuit which actually enables this selects this chip if the address is in the range, in the desired range, which is from 0x00 to 0x0F, and not select this chip if the address is out of range. Okay. So now the question is how we can develop such a logic circuit. So we will try to answer this question in next set of slides. Again, if anyone have questions at this point, please let me know. And I'm switching to next set of slides. Which is actually our today's set of slide. Okay. So before answering that question, that how we design such a logic circuit which enables or which selects a given memory chip when it sees that an address is placed on the address bus by CPU which belongs to the range of that memory chip and doesn't enable it otherwise. To answer that question, we first need to talk about logic gates. Okay. So we'll first talk about logical AND operation, and so there are two things. One is logical AND operation and one is AND gate. Let's first talk about AND operation. So the AND operation is like it has two inputs A and B on which you apply the AND operation, and the AND operation is indicated by cross symbol here. Actually, it is traditionally it is indicated by a dot, A dot B, but here they have put cross, but okay, for time being we can accept it. So how this operation works. So before even explaining this, we know how addition works, right? Like we have a plus b, how it works. Like let's say the value of a is 2, value of b is 3. So 2 plus 3 is 5. We simply add the numbers and we get the result. Now, so plus is an operation here, and is an operation. So we have just like add, we have two inputs A and B, but instead of doing the addition, we are doing the AND operation. Okay, and how AND operation works? If both inputs are zeros, A and 0, if both are 0, output is 0. If any one of A or B is 0, 0, 1 or 1, 0, output is 0. And output is 1 only if both inputs are 1. So basically we are saying that output be 1 only when both inputs are 1. If any one of the inputs are 0, the output will be 0, right? So this is AND operation. And actually in digital design or in digital devices, AND operation is implemented by a piece of hardware which is named as AND gate. Okay, and this is the symbol of AND gate here. This is symbol of the AND gate. It has two inputs and it has one output which is named as AB. So A dot B actually. So this is how AND operation works, and this is the symbol of the AND gate. Now AND gate internally is how to say, made up of transistors, but we are not going to that lower level. Okay. So there is another logical operation which is named as OR, which basically says, and it is indicated by plus symbol here. Okay. And again, here you have two inputs, A and B, and A plus B is the like output of the operation. And the output of this OR operation is 1 if any one of inputs are 1, like either A is 1 or B is 1. So if any one of them is 1, then output is also logical 1. If and the output is 0 only if both A and B are 0 here, right? So this is AND OR operation, and the symbol for OR operation, symbol for OR gate is this one. And on the input you have two A and B, and output you have A plus B. Okay. There is another operation which is known as NOT operation, logical NOT operation. So actually it is just complement. So if the input is 0, then so A complement will be 1. And if input is 1, output will be 0. And this operation is indicated by NOT gate, and which has this particular symbol here. Any questions? Okay, another logical operation is NAND, which is basically same as NOT AND, which basically mean that first, so if you want to do NAND operation on A and B, so what you do is that first you find AND of A and B, and then on the result you apply the NOT operation, right? So it has this truth table. So okay, someone has okay. Uh, So first the output is indicated like with this symbol AB, and then on both of them you have a bar, which is also known as which called as complement, AB complement. Okay. So if actually it is just negation of AND. So let me just write here maybe AB to make it easy for you guys to understand, right? So let's first find AND operation result. So if 0 0 is 0, output is 0, 0 1 0 for AND, 0 and here 1. And then after that we do NOT. So this actually this bubble at the end of the AND gate indicates NOT. So when you do NOT, 0 becomes 1, 0 becomes 1, this 0 becomes 1, and this 1 becomes 0. Okay. So and this whole is symbol of NAND gate. Okay. Any questions? Okay. Exclusive OR operation. So exclusive OR operation basically says that the output will be 1 if either A or B is either A or B is 1, but not both of them. If both inputs are 1 or both inputs are zeros, then the output will be 0. Output will be 1 only and only if one of the input is 1. So for example, here A and B, out of A and B, only one of them is 1. So that's why we have an output of 1. But in other cases where both inputs are zeros or both inputs are 1, the output is 0. And this is known as exclusive OR. Okay. And this is the symbol, gate symbol for the exclusive OR operation. And this is how you indicate it in writing. Okay, now let's come back to our same question. Remember, we said that we need to design a logic circuit or a logic which uh, enables this chip or selects this chip only when the address is in the desired range, and otherwise it doesn't select this chip, which basically means that if address is in the desired range, then here the logic circuit should output 0, and if the address is not in the desired range, then the output of the logic circuit should be 1, right? So how can we do that? So first you need to write the address range in binary, right? Let's stick to the same example, which I showed you on the one node. So what was the address range of our address range in that example? It was 0x 0 0 to 0x 0f, right? So first thing is that you need to write this address range, the desired address range of the memory chip in binary. So when you write it, what you will get? You will get here all zeros. You will get 8 zeros, because when you remember, when you convert hexadecimal to the binary, you replace each hexadecimal digit with 4-bit binary. So I replaced them with 4-bit binary. And for this 0x0f, you have 1, 1, 1, 1, and then 4 zeros, right? And then after that, from address, so you just have written. So this is actually another example. So actually the same example. Okay. So then what you do is that you separate the fixed part of the address. Which part of the address is fixed? I can now follow from here. So this part is fixed, right? Fixed means these bits are never changing the value. These bits never change the value, right? So identify the fixed part of the address. Okay. And then use a NAND that is design a logic circuit whose output activates when the fixed address is given to it. So when you now we need to design a logic circuit such that if we give this input to the to that circuit, the output is always one. Remember what are these inputs? These are A4, A5, A6, A7. So these are address lines, address 0, A1, A2, A3 up to A7. Now we focus only on the fixed part here, right? So now how you can remember what was the operation of the NAND gate? Let me go back. Yeah, here. So this is the NAND gate, right? So it is, uh, you get the value of output equal to 0 when all the inputs are 1, right? See, when all the inputs are 1, right? Now we need to put, let me do it here for you guys. So I want to design a NAND gate with 4 input. And this one is, let's say, A4, and this is A7, right? But if I put here 0, 0, 0, 0, then the output will be 1. But I actually want the output of 0 when all of these inputs are 0. How can I do that? If I go back to the logic gate, I need to have all the inputs equal to 1. How I can make all the inputs equal to 1? Anyone who can suggest? Put a NOT gate, yeah, just invert them, right? Because I know that they will never change their values. Their values will always be 0, right? I know it. So I can simply put a NOR gate, a NOT gate on the input, which I can indicate by putting a bubble here. So if I am putting a bubble here, it's mean just put a NOT gate. So this is what is done here. Maybe I should have not run in the same area, but you can see here they just simply put a bubble. Okay, now if you simply put a bubble, so what will happen that if there is an address generated within the range, this chip select signal will always be 0. But if the address is generated out of the range, the address will be the chip select signal will be 1. uh, Let me try to do an exercise to prove this to you. Let's go back to again to our notepad. Why I keep saying notepad? It's not notepad, it's OneNote. Okay. So this was our logic circuit, right? And it has, let's say here it is A4, and I'm not writing A5 and A6. I'm writing only A7. So you guys understand A4 to A7, right? And this goes to chip select of the memory chip, right? Now give me any address in any 8-bit address. Anyone who wants to give an address? Any 8-bit address. You can write it in the chat box. Be quick, guys. 12. Is it decimal 12? 0x12. Okay, thank you. He said 0x12. Okay, so let me write here 0x12. Now, in our example, is it in range or out of range? It is out of range because why? Our memory can accept addresses only in the range 0x00 to 0x0f, right? So it means that for this address, the chip select signal should be equal to 1. Now, let me convert it into binary. So when I convert into binary, it will be 0, 1, 0, 0, and then 0, sorry, 1, 0, 0, 0. So the binary of this one is this, and the binary of 2 is 0, 0, 1, 0. Now these are A4 to A7, right? So here I am putting 1. Oh, sorry. Here we also have bubbles. So here I'm putting 1, 0, 0, 0. So if it is 1, so it's mean that here the out what will happen based on the NAND operation. So I will get an input of 0. So if any input is 0, output will be 1. So memory will chip select will be not selected. Now if I am let me select an address within the range of the memory. Let's say I select 0x0a, right? So if I convert it into the binary, it will be a is 10, right? 0, 1, 0, 1. So this is binary of A, and then 0, 0, 0, 0. So this is A4 to A7. Now if I put here all zeros, so if a NAND gate has input of all zeros, then chip select will be 0. Okay. Any questions? If you don't understand how this was working, let me know. Clear? Okay. Okay, now here is an exercise for you guys to do. Suppose that you need to design an address decoder for address from 300 hexa to 3FF hexa. Okay, so so H here mean it is a hexadecimal address 300 to 3FF. Okay, and the address decoder basically mean you need to design a similar and NAND gate, so which gives you chip select signal of 0 if address is in this range 300 to 3FF. Okay, so how you are going to do that? uh, do it on your notebook. You have how many minutes? 3 minutes. 3 minutes to do this. Okay, do the exercise in 3 minutes. I know slides are available online, but don't look at the solution. Try to do it on your own. And when done, let me know. If you are done, let me know by sending a text. Okay, thank you. Okay, let's wait for a couple of more people to complete and then we can go to the solution. Good. Okay, okay, good. Good. Now let's have a look at the solution. So again, same thing, write the address in range in binary. So if you write in the binary, it will be look like this, right? From A0 to A11. And then so you separate the fixed part of the address, which is this one. And then you design the logic circuit. So remember, for NAND gate to have an output 0, we need all of its input to be 1, right? So two of the inputs A8 and A9, they are already fixed to value of 1. So we don't put bubble for them. But two inputs A10 and A11, they are 0, fixed at 0. So we need to invert them, right? By putting bubbles on their values. So A10 bubble and A11 bubble, invert them and then give them as input to the NAND gate. So then now this is how your address decoder will look like. Now this address decoder will give you an output of 0 whenever an address is in this range, right? Within, like, it is greater than equal to 300 and less than equal to 3FF. But if the address is out of the range, like, which means less than 300 or greater than 3FF, then it will give you an output of 1, right? Done. Okay, anyone who had a different solution than this one, a different decoder? I mean, if your solution was incorrect, I just want you to, like, let me know so that I can walk you through it, like where you make the mistake. No? Okay, so another easy way of doing this is that you simply put a NAND gate here, and the places which have 1, you don't put bubble for them, and the places bit position which have zeros, you put a bubble for them. So simply replace zeros with bubbles on the input of the NAND gate. And for ones, you keep as it is. You don't invert them. Okay. Again, another exercise. Design a decoder for memory address from 0x50 to 0x5f. Again, let's use only 2 minutes for this. And when you are done, notify me. Wow, this was quick. Okay, let's wait for some other people to complete. Good. Good, guys. Good, good. Let's go to the solution now. Good. So again, do the exactly same thing. Actually, even without converting the binary, you can simply, by looking at hex, you can see, okay, which part is like fixed. 0x y is fixed. 0 and f are changing, right? So anyway, if you, for your easiness, if you want to convert to the binary, you can convert. So after converting the binary, you find that, okay, this part is fixed. So then you feed this part into the AND input of the AND gate. And if the input is 0, then you simply invert it here. And that is how you design the decoder. Okay. Any questions? Okay, now let me go back to let me just try to refresh your mind with the figure where of like internal details of the microcontroller. Remember, we had different components, like we had CPU, memory, IO devices. We talked a little bit about memory characterization, its pin, how we connect memory with the CPU, why we need the address decoder, right? Now let's talk about the other components of the microcontroller, and one of those component is the CPU, right? So initially in that figure, I don't want to go back because I need to then open the slides again. But if you remember it, in that figure we just had a block diagram or a block for the CPU. But then it is not that simple. Inside the CPU, you have other different components within the CPU. So what are those components? You have a register which is named as program counter. I will explain what is the job of program counter. You have a component which is named as instruction decoder, another component named as ALU, and registers. Now, the job of the PC or the program counter is actually when you run the program. Remember, from our previous lab, we were writing assembly instructions, right? And those assembly instructions were at different, when you write your program into the memory of the microcontroller, they go into the memory location. Let's say the first instruction goes to location 0, next instruction goes to the location 1, and so on and so forth, right? So if first instruction goes to the location 0, then in the PC counter, so when your program starts executing, let me draw it here to make it simple. So let's say these are like each line indicates an instruction, and they are put in the memory when, just like when you wrote your code in lab 1 and downloaded in the AVR microcontroller, so it went into the memory. And let's say this is first line is first instruction, and it is saved at address 0 of the memory, and this at address 1, and this at address 2, and so on and so forth, right? So when AVR executes this program, what does it do? It first reads the instruction from the memory at location 0 and executes that instruction. Then from the next location, which is 1, and then next, which is 2, and then next location, which is 3, and so on. Now, the job of the PC register is to hold the address of the next instruction to be executed. So at the start of the life, at the start of everything. So initially, PC will have 0. So this instruction will be executed. And after that, PC will be incremented to contain 1. So then this instruction will be fetched and it will be executed. Then PC will increment to 2. Then next instruction will be fetched and executed, and so on, right? So this is the job of the program counter. It just holds the address of the next instruction in memory, in the code memory, which will be executed. Instruction decoder. Now the instructions which you fetch from the memory, they are different type of instructions. Like you are saying load some data into a register, load some value into a register, or you are saying, okay, add two registers, or you are saying increment two registers. But then in order to, now as human being, we understand what is the meaning of each of these instructions. But for the digital hardware, it first need to decode that instruction to understand what to do. For example, if the instruction says load immediate value of 5 in register A, so it first need to look at the binary code of that instruction, and then after looking at the binary code, the hardware understands, oh, it wants me to put value of 5 in register, let's say 1, right? And let's say there is another instruction at address 1, so which says, okay, add register R1 and R2. So again, it will have a different binary code. So instruction decoder will look at that binary code and then understand, okay, this instruction wants me to add register R1 and R2. So this is the job of the instruction decoder. Okay. But again, in this figure, we are simplifying everything. Instruction decoder simply looks like a block. Actually, it is like a logic circuit, just like we using like gates, we develop the circuit which is responsible for doing different kind of things. Okay, not only gates, but also there are other components like latches and so on, but uh, it is a logic circuit. Okay. ALU, this is arithmetic logic unit. So for example, if you say that, okay, PC says that, okay, fetch an instruction from address 0, and then that instruction is decoded by the instruction decoder and finds out that this particular instruction wants to add the register R1 and R2. So the job of the instruction decoder is just to make sense of what the instruction wants me to do, but it doesn't actually performs that operation. The job of the ALU is to perform that operation. For example, the actual addition of content of R1 and R2 will be done by ALU. And arithmetic logic unit will be doing both kind of operation. Arithmetic operation like addition, subtraction, multiplication, and also logic operations like AND, OR, NOT, exclusive NOR, and so on. Okay. Registers. So registers are actually, they are the data holders. The data which you read from memory, it is placed in the registers. Are the data which you write into the memory is actually written, like it is the source of that data is register. So the data which is fed into the ALU, it always comes from the register file. So the combination of all the registers is known as register file. So the data, like when you want to say, okay, add register R1 and R2. So then these two registers will be added. Sorry. Any questions? Okay, I think we have 7 minutes, so I can at least, I think I can complete this slide. So now in this slide, we are going to look at how a computer works. The basic idea is same, but at a very like it is applicable to both microcontroller and CPUs. Definitely, there will be other things, other details which are how to say abstracted out in this figure. But let's keep things simple. So let's say you have this program, put 17A. So basically, you are saying read data from the memory at location 17 and put it in register A. Then put register in B, register B. Then put the data, read the data from memory location at address 6 and put it in A. Then add A and B and put the result back in A. And then you are saying put the result value of register A into the memory at address 7. Okay. So now let's say you wrote this program in your Arduino IDE, and then you say, okay, you load it into the code memory of the AVR microcontroller. So then this will be converted into the each instruction will be converted, each instruction will be converted into a binary code or the machine code. So let's say that machine code is represented here. 31 hex is the machine code for the first instruction, this one. C4H is the binary code for next instruction, and so on and so forth. And each instruction is stored in memory location. First instruction is stored at location 0, second one at 1, and then 2 and 3 and so on. Okay. Everyone with me until this point? Okay, now we want to look at that how this program which we have burned in the memory, code memory of the AVR, how it is executed. When it executes, what happens, right? So initially your PC contains the value of 0, pointing to the first instruction. Okay, so first this address PC0 is actually the address of the first instruction, right? So you put that address on the memory bus. So when you put it on the memory bus and then you say, I want to read from this address. So basically you read from the code memory, right? So you read the instruction from the code memory and bring it into the CPU. So here you are enabling the read signal. Yeah, yellow mean that you are pulling it down. Okay. So now what happens that this 31 hex is read and it is brought this instruction is then decoded by the instruction decoder, right? But here we don't have internal details of this decoder. We just keep it like simple block level diagram. Okay. And then what happens is that your PC is incremented. Okay. PC becomes 1. But before you execute the next instruction, actually, this is not how things happen, but we just want to keep it simple. But before the next instruction executed, you have this because you are executing the first instruction, this one, right? And this says read the data from the memory at address 17. So your CPU puts the address 17 on the address bus, and then it puts this read signal low. So if it puts read signal low, it means it's want to read from the memory. So then the data is, let's say it means that this address actually enables the IO device 17, right? So if it enables this device, the data is read, and that data is 9, right? And we need to put it in the register A, right? So it goes to register A. Now we are done with the first instruction. Now PC contains the value of 1. So PC will put this value on the address bus. So then the instruction of the second instruction is read from the code memory, which is C4 hex, C4H, right? So then instruction decoder will decode it, and then it will find, oh, it is telling me to move the data from register A to register B. So then what happens is that same data is copied to register B. Now A and B both have same value. Now PC is incremented to 2. So this address is now placed on the address bus. And again, the read signal is held low. So you are reading the data from the next location, which is 26 hex. So instruction decoder decodes this instruction 26, which actually says read the data from memory at location 6 and put it in A. Okay. Remember what is 6? 6 is here, right? So you put the address 6 on the memory bus, pull down the read signal, and then the data is read and it is placed on the data bus, right? But we are not yet done with this instruction because we need to put the data in register A. So then this data is placed in register A and we are done. Now, the next value of the PC is put on the bus, address bus. So we read from the memory location 3, and it has the machine code of 81, which is actually this next instruction. So it is saying add A and B and put the result back in A. So now what will happen is that 5 and 9 both will be sent as input to the ALU, and the result will be put back into the A. So if you do 5 plus 9, it is 14, which is E in hex. Okay, so that's why we have E here now. Now then PC is again, the next value of PC is placed on the address bus, and the data is read again. So which is the next instruction, and this time we are saying, okay, put the value of A in the memory at the address 7, right? So which means that we are going to write the data in the memory. So this time we put the address 7 on the address bus, we put E on the data bus, and we pull down the write signal, right? So now this time what happens that your data E will be written in address 7 here. Okay. So logic circuit here is not, it is shown only as a block diagram, but definitely you will have a actual logic circuit to enable the chip select. So this is how your program will be executed. Any questions here? Now, after going through this animation, you should have an understanding of what the job of program counter register is, what is the job of address bus, data bus, control bus, how memory chip is selected, how different operations are performed, what is the job of registers, RALU, right? So if you have any questions, let me know. Okay. If no questions, then let's stop here. And then on Thursday, we will continue with the same set of slides. Actually, we'll continue from the same point. Okay. The lab 2 is released, and I have also posted the video. Uh, just a quick question. Does anyone of you, is there anyone who thinks that lab 2 is hard and uh, you need extra help to work with the lab 2? Or you need any help in understanding even lab 1? If you need any help, I have office hours starting in 15 minutes from now. So you can join me there. I don't think I did lab one correctly. Okay. If you okay, so if you need help, okay, okay. If you need help in understanding the lab one, or if you think that you were facing some difficulty, office hours will start in 15 minutes. The link is available on the syllabus page of the course. You can simply click on that Zoom link and I will be available there and I can help you to understand the things which you didn't understand. Okay. You think you were okay. If you were graded wrongly, then please contact the TA. The TA, you know who is the TA for your lab section, right? For the Tuesday lab, it is Nazia, and for the Thursday, it is Farzana. So please contact them if you think that you were graded wrongly. Anything else? No? Then let's stop here and see you in next lecture.